So, good evening, everyone. We can start our today's session. So, first of all, I would like to welcome you all on fourth International Faculty Development Program on Data Analysis. So, we have with us our expert, Dr. Shweta ma'am. So, we welcome you, ma'am. So, today, ma'am will deliver lecture on topic multivariate methods on with hands-on Python. So, ma'am is currently working as assistant professor Maulana Abdul Kalam Azad University of Technology, West Bengal. So, we welcome you, ma'am. Now it's up to you.
Thank you. Thank you so much, Dr. Chandra. Good evening, everyone. I, Dr. Shweta Mishra. First of all, before proceeding for the hands-on with Python and the topic, I would like to thank to the organizing team for their thought and organizing such an technical session for all of you. So, very much thankful to the organizing team, Dr. Chandra, Meadows Agriculture, and your team. Thank you so much. And uh, again, giving me an opportunity to put some idea uh, related to that, your fourth International Faculty Development Program on Data Analysis. My today's topic is multivariate methods with hands-on Python. So here we will discuss about the topic that multivariate methods, how it is helpful in different sectors, like we can say engineering, medical, agriculture, different domains, manufacturing industries, so on and so forth. But before that, proceeding to that, we first understand the learning objective. What is our idea, like what is our objective to understand from this session? So the idea from this session, that what we are going to understand is that we will able to develop one analytical skill that help us to extract meaningful visualization, values, details from complex or big data. Then here we will use some Python libraries that will help us to apply machine learning, the advanced technologies, and get the results. Then if you can see that before that, what is that multivariate analysis? So we have to understand that what is multivariate analysis. So we can say that it helps us to understand the fundamental concept of mathematical foundation. uh, that mathematical foundation help us to make that methods as a powerful tools or technology that will help us to analyze the correlated data or correlated variables, that how they are working together, are they totally different or something. Then we will apply PCN clustering. These are two algorithms. It help us, from this session, you will be able to implement that PCN clustering in your particular domain that you are working on. Then the next thing is that what if the algorithms, the methods we are learning, what if they fails? So then we have to understand that what are the other options that we can proceed, or how we can make corrections to get that answer from that. Then again, using some nonlinearity alternatives, and then finally we will use some Python libraries to implement all these things. So next is that why we are going to use that multivariate analysis. So the idea is that it will help us to provide the relationship between complex variables, and also using these relations between the variables, we will able to find the hidden patterns that were not easily, or we cannot easily see that. And then ML foundation, ML machine learning, it help us to understand that and implement that algorithm, so that we can decide, or we can get the new data. Now here that we will, with the help of machine learning, machine learning, we will able to understand feature engineering. We can say that extracting some uh, really informative or useful data, actually important for, then we can understand that from all that big data, which data is important and how we are going to use that. And then their visualization, because as a human, it is very easy to understand or remember or get an idea about once we see the things instead of the numbers. So with the help of machine learning, we will able to visualize our data. Now, setting up Python. So how we can set up Python to use that? So for that, we will here I'm using Anaconda distribution because it have most of the related libraries modules are there. So no need to install it further. So you can say that it is one in all that we have most of the libraries. What are the libraries or modules that we are going to use? We will use pandas. Panda, it will help us to make the data frame. Then NumPy, numerical Python. To visualize beautiful pictures and all that, we will use Matplotlib and Seaborn libraries. Scikit-learn, it helps us to import the machine learning algorithms even without writing the whole code. So this is the beauty of Python. You can say that here it is not required to write whole the things. You can automatically, like you can easily import that libraries, that algorithms, and it will work for you. And then science by statistics, since we are using some statistical methods, so for that we can easily import that methods with the help of science by stats. So here I'm stop here I'm stopped to the this presentation, and then I'm directly going to the hands-on so that you can easily understand the thing that how we are doing and how the mathematics is related, how the data are working. So let me connect to the Python hands-on, Python programming language. Is the screen visible?
Yeah, yes,
Yeah.
ma'am.
Okay. So here, see, when we are going to do, when we are talking about data, so the idea is that, or you can say that the question is that, that what is the data and how we are going to use that data. So since Meadow's agriculture, as we got an information that most of the students are related to that agriculture and medical field, so I'm taking examples of that only. So if you can see that for the agriculture one, how you can see that if you are looking for a patient, when you are looking a patient, that what kind of data or information you can get. Or if we as an agriculture expert or researcher, if you wanted to see a field, then what kind of data or information you will get from there. So if you can see that here we can simply see that in the agriculture field, here we will get some data like soil pH balance, that nitrogen content, phosphorus that is given as the you can given to the soil to fertilize them, then rainfall, then temperature, humidity, integration hours, lots of things. So we, for our data, all these you can say that the features or variables as the data of we needed. And we consider, suppose for different fields or different forms, we will have a huge data. Similarly for any patient, if you can see that what kind of data we can have. So there we may have the age of the patient, their body mass indexing, their BP, their blood glucose, cholesterol, hemoglobin, and etc. So we can see that at least for a single patient, we may have 10 to 20 kind of type of data. So when I'm saying that type of data, you can say that type of data is that you can say that our property or attribute or variable, and the number of patients, you can say that can be any number of patients. So with increasing number of patients, we will have a use data. Similarly, for the agriculture field, we can see different 10 to 15 number of variables for one specific farm or field. So if we have multiple number of farms and field, then how we can understand that data and all. So the problem is that we can see that the problem is that the dimensionality. It means when we are saying that we have a 12 kind of information for one specific field, so simply for 50 fields, 15 into 50 into 15, so it's a huge data, highly dimensional. Similarly, for a patient, for a single patient, we have 15 to 20 variables, different informations. Then for 100%, 500%, so the data is highly you can say that's a big data or huge data. So when we are saying that hard to visualize, obviously, see, as a person, we can simply visualize the 2 dimension or at most 3 dimension with the pen or paper. But when someone asks you to draw to the some plot for 10 specific patients data, that will be difficult, or 10 specific fields data, then it will be difficult. Sometimes we can see that few datas are highly correlated. So you can say that in that case, when the datas are correlated, it means the increase of one variable impact the increase or decrease of the another variable. It means this is related. So sometimes we may have huge data, and that data may not be useful for further. So how we are going to remove or avoid the data, that is also very important. Then understanding then that from all those important information that we have, which are crucial, which are not or we can keep the some data that for further, and which are crucial for now. So that is again, it's a very important thing to understand. And then another thing is that sometimes there are some methods, they are very helpful while we have a few number of data, 3 4 patient, or you can say that 1 or 2 fields. But when the number of patients are high or the number of fields are high, when we are talking about a bigger data, then all these methods are labs. In that case, we need some specific methods, machine learning, artificial intelligence, that easily work on the same way that it was working on a smaller data. On the bigger data, it is not impacted by the size of the data. So here, our methods that we are going to discuss, PCA. PCA, it means principal component analysis. So when we can work, use that. So when too many correlated data, variables, and when it is difficult to understand or visualize that impact, then we can use PCA. What it do? It simply reduce the number of variables from 10, 15 to, you can say, 3 to 5 meaningful variables, meaningful components. And then cluster analysis, you can say that clustering, it means that we are simply segregating the whole data in 2 or 3 different domains, groups, or clusters based on their related uh, results or information. So before going to that here are few that variables that we are going to use. So that I already discussed, but still we can say that variable or features for the column wise information. So we will write it as the soil pH, blood pressure, glucose level, all that. Observation or sample. So we can say that it will be represented as a row wise information, where one field or one patient data will be row wise. Then the dimension, the total number of variables, then how they are related to each other, that is variance, then how they move together, that is correlation. Then we have to understand the direction of maximum variance, that is eigenvector, and then eigenvalue, amount of variation in that direction. So here, how the principal component analysis, the definition, the understanding. So before going to the definition, let me make you understand that how PCA works. PCA, principal component analysis. Just assume that you have, like here I already wrote that, but see, if you have a 3D object, and for that 3D object you have to put some light so that you can get a shadow in 2D object. Now try to understand that PCA is the idea that how, what should be that angle to get the specific information of a 3D, three-dimension figure into the two-dimension. So you can say that PCA is a statistical technique that transfer a large number of correlated variables into smaller number of uncorrelated variables called principal components, while preserving most of the, or you can say that much of the original information intact. That is very important, because PCA is not only reducing the number of variables, but it maintaining the quality of the information. It is not that while using the PCA or reducing into the lesser number of variable, we are losing the important information. So here, how PCA works. So the mathematical concept and all that. So the first thing is that when we are going to use the principal component analysis, PCA method. So the first idea is to that standardize the data. So before doing anything, we must ensure that all variables on all are on the same scale. This is very important, because sometimes not in standardizing the data, it may lapse the information, it may provide the information which is not actually relevant, or that is not based on the quality, that is only based on the quantity. So here, if I can say that we will mention that soil pH range from 4 to 8, or you can say that crop yield range from 500 to 800 kg per hectare, or we can change our blood pressure data into 60 to 200 mmHg, or something like that. Then we have to make sure that all data are in a same scale. If we will not, as I said, if we will not equalize or standardize their data, then there will be a problem that the variables which have higher number of data, they may dominate the whole data set, and we will get the result according to that variable. That variable may not be that much impactful, still we are getting the result, and the results are not accurate. So that's why the first step is to standardize the data. Now, what is the meaning of standardization? We can say that to standardize the data, our idea is to, we have to make sure that the mean of the data is 0 and the standard deviation is 1. Now, if here we can see that you can simply see that the mathematical formula is that for any specific variable, we are saying that the original value minus their mean value divided by the standard deviation. So we will use this formula to standardize our data set. And after standardization, we can see that most of the, or all the data should has a mean of 0 or a standard deviation of 1. Now, second step is that compute the covariance matrix. This is another important topic, that once our standardization is complete, we will calculate how every pair of variables related to each other, because PCA work on that correlated or correlation of the variables. If there is no such correlation, then we will not able to apply the PCA methods. So here that we can see that the idea is that does nitrogen increase the soil pH balance, or putting some phosphorus into the field, will it affect the soil? Will it impact the growth or the breed, something like that? Then similarly, like if we are talking about like blood pressure for the medical related field, so will that increase of blood pressure will impact the BMI, or the higher age impact the BMI? So that is required, that how different variables are correlated to each other. Now here, if you can see that this is simply this formula represent that the covariance between two variables, that we can say that their depth item is simply related as that if both xj and xk increases, we can say that more than one or average of the same time, then we can say that they have positive covariance. It means they have similar trend. But once we can see that when one is increasing, another is decreasing, it means we can say that they have opposite to each other, or opposite impact. While if we have zero or totally different, or we cannot find a specific pattern, in that case we will say that the variables are highly uh, non-correlated or uncorrelated. The next step is that eigenvalue decomposition. This is you can say that the mathematics steps we are discussing to understand the PCM. So here we decompose the covariance matrix into two things: the eigenvalues and the eigenvectors. Eigenvalues are, we can say that this is the multi-dimensional shape of the data we have. So you can say the data cloud or data points, and then the direction of that data points, data shape is called the eigenvector. On that, the axis along which the data is most spread out. Eigenvalues are, we can say, amount of spread in each of these directions. The first eigenvector points in the direction where the data varies most, we can consider as a principal component 1. Now here, if you can see the formula, the how it will work. So here, if you can see that the sigma is the covariance matrix, small v, it represents the eigenvector, while lambda is eigenvector v, it means direction, while lambda is the eigenvalue, you can say that shape of the data clouds. As I said that we arrange the eigenvalues in their decreasing order. The highest value will represent as a PCA component, principal component 1, 2, and then. Now, this is another one important topic. Important thing is that how we are going to calculate the percentage of the principal components. So for that, we have proportion of variance explained, PVE. So here we can calculate that. Suppose we have 8 variables in the original data set. Now, for all that 8 variables, we have to calculate that with different algorithms, different rules to their percentage, and then this is the cumulative one. So suppose this is for first PC1, principal component, their percentage. Then PC2, their percentage. And since we have 8 variables, so cumulative will be, we are going to add one by one, like PC1, then PC2 will be the PC1 plus PC2. Then PC3 will be PC1, PC2 plus PC3. This way we will proceed for the cumulative PV. Now here, if you can see this here, each PC stores, now here, if you can see that here, this mu1 or the weight assigned to the standardized data. So this PC1 is, each PC score is a weighted sum of all standardized variables. So suppose we have 8 variables, so the weight assigned to each standardized, so that multiplies with the standardized data value. Now here, before going to that, here you can say that simply, as I said, that we are going to use Python programming language. So here I'm just importing different modules that we are going to use now. See, you can see that here that I have import NumPy. I just told you that NumPy numerical Python, since it's a 5 character, so just to make it as a shorten, we have used as a NP. Then pandas for data frame, tabular form. Then you can see that these are few the visualization and all that. And so we can simply executing this, and then we can see that we are, see here it is showing that the data is the commands that we have given on the Python library cell. Is it executing? Yes, it is executing. Yes, 1, it means it's already executed. Now here you can say that all libraries loaded successfully. We have the NumPy version, this one, and the pandas version, this one. Okay. Now here for the agriculture one, I have considered one data. So the data is this one is clear to everyone. Is there any doubt? Anyone? No? So here, suppose for the agriculture data, we are considering a problem. So what is our problem? We are considering that we have 30 farms across a region, and we have total 8 variables for each farm. So this form, that what variables are? That variables are soil pH, we can say that nitrogen, phosphorus, rainfall, temperature, irrigation hours, organic matters, yield turn, all these information. These are the units represented by the data. So what we have given here with the, for the PCA, applying PCA, we have put some data, and since we are using, as I said, that panda, so here you can see that we have our data set. As we are considering for 30 firms, but as you can see that since 30 forms we will get a use data, but here what I'm just showing you first 10 data set or first 10 farms data. So here you can see that soil pH, farm 1 6.25, farm 2 7.40. Similarly you can see that here each column, these columns are our variables that we considered for different forms. So here you can see that row wise information. Now, so here, then we have get the descriptive statistics. It means we have to check that the data we are considering, is it actually for all firms or not? Is there any missing data? Because that is also important. We need all the data so that we can proceed. So here, if you can see that for each variables here, the count, it means how many forms we are considering. So here you can say that it's a 30 for all. It means we have data for all 30 forms. Then mean, we can say that what is the soil pH mean for all 30 data. So if we can say that from all 30 data, we have the mean as 6.38. What is the standard? Standard 0.56. Minimum, what is the minimum soil pH for any form? So here you can say that it is 5.54. What is the maximum soil pH for any form? That is 7.44. Similarly, you can see for the nitrogen, phosphorus, rainfall, all that data. Then next, what we have done that here, we are simply construct a correlated plot. Because if you see that understanding the relation is very important, that how one variable impact other variable. So suppose here we are considering that how soil pH or nitrogen kg impact each other, nitrogen impact each other, or how the rainfall and the temperature impact each other, or are they impact the on the farm or not. So here you can see that here with the help of, as I said, that plot let we have using matplotlib. So with the help of this one, you can say that we are plotting a heat map for the correlation matrix. And here you can see that this is our correlation matrix. Let me execute it so that you can see. Yeah. So if you can see that here, this correlation matrix, if you can see that, can you see here? This row wise and column wise, we are considering our variables. So here, if you can see that soil pH with soil pH is obviously that is the relation is 1. So if you can see that the diagonal will be exactly 1, that's why we are not writing that. Our aim is to, motto is to find the relation, the correlation between different variables. So here if you can see that here it represents that from lowest to the highest. So here if you can say that, see that here you can easily see that how nitrogen, phosphorus impact with the soil, or you can say that how phosphorus affected by the yield, or how rainfall is affected by the organic matter, or you can see that how organic matter is impacted by yield. So here you can see that the dark green represent the highest correlation, while the red one represent the lowest correlation. Now if you can see that the negative one, it means now here irrigation and rainfall. So you can easily understand when there is a huge rainfall, then no irrigation required, or if irrigation required, it means there is no rainfall. Or you can simply see that for the immigration, that you can see that irrigation, that you can see that organic matter. So if there is a irrigation required or less water, in that case that how the less water impact the organic materials exist in the soil. Similarly, that rainfall and then the temperature, how they are affected or related to each other. So here this is how we can. Now next is that as we standardize the data, that is very important, because without standardizing the data or putting the data on the same scale, we will not able to proceed further. So here I'm just running this code, and then you can see that earlier we have this data.
Unknown caller.
Sorry. Earlier we have this data. You can see that the first row of the data. Now, when we did this standardization, so here you can see that this is the data, standardized data, first 5 rows. Here we are getting only first 5 rows. So here it starts from 0. So 0, 1, 2, 4. Now, if you can see that mean of standardized data, that is 0 for all 5 rows that we have considered. Similarly, standard of standard deviation of standardized data. So here you can see that it is almost 1. 1.017, you can say that it is almost 1. It means we can see that our steps are completed, that standardization and standardize the data. We have also find that the relation, that how they are affected, and then we are going to get the, now see, then here you can see that the components are already divided. Since we have 8 variables, so here you can see that 8 components. As you have already seen that how we can calculate it. So see here the formula, this one, that how we can calculate the uh, percentage. So for this one, you can see that the PC1 is calculated. So here for the PC1, principal component 1, we have calculated the variance percentage is 43.09. Cumulative is again 43.09. Now for the principal component 2, the variance is 24, but cumulative, it means we are going to add 43 plus 24, you will get 67.30. This is the Cassel rule. Similarly, for PC3, principal component 3, we can see the variance is 10.95, and then cumulative will be 67 plus 10, you will add, you will get 78.25. So this is the way we can say that these are the this way we have already calculated our principal components, then we have calculated the variance and then the cumulative variance. Then we are calculating the here. Oh yes. Now here, now we are seeing the tree plot. Now here, if we can see that from these plots here, what we are calculating, the PC components, the principal component. So here, if we can say that the principal component with respect to the eigenvalue. So if we can say that considering the principal component, 8 principal components, and here with respect to the eigenvalues, so if we can see that the first 2 principal components are more than 1. So here generally for the Cassel rule is that we will consider the principal components only those which are greater than 1 or whose eigenvalue is more than 1. So here you can say that here PC1, principal component 1 and principal component 2, choosing these two only, we are able to cover around 80%. You see that the cumulative, PC1 and PC2, we are getting around 67, 68%. And first 3 principal component, it will give you around 78%. While first 4 PC4, it will give you around 88 to 90%. So it means instead of understanding all 8 variables, proceeding for all 8 variables which have high dimension, we reduced into the principal components. And this is another, you can say that cumulative percent variance with the principal component. So we can say that how it increases. PC8, it will be obviously 100% because cumulative, but our idea is to find at least 70 to 80%, so that is good enough. Now the next thing is that with the help of these data, then we are going to create the heat map. Then again you can see that here PC1. Now see, if you remember earlier we did the heat map plot here. This is the heat map plot for variable to variable. Now these 8 variables we have reduced into 8 principal components. Now here we can see that 3 to 4 principal components are enough to provide 70 to 80% accuracy. So here again we construct a heat map with respect to the principal components. So here you can say that now here we will get an idea that how principal components are involved into affected by that or which variable. So here you can see that how principal component, most of the variables, like if we can say that the highest values are the you can say that that's soil, pH, nitrogen, phosphorus, rainfall, organic matter, and yield. It is involved into the PCA1, while PCA2 focused on rainfall and organic matter, while PC3 focused on the temperature and you can say that organic matter. Now here, this is the final, this plot, we can see that yes, this is the important that plot that we have constructed from here. So since we get an information that which variable impact the principal component this way, so here we have considered a scatter of the forms. We have total 30 forms, so we are going to use that 30 forms, and then we are labeling some forms, that how we can understand that which form is that. Then we are getting some arrows, because this provide us that information about the relation of that forms. So here, if you can see that this principal component 1 versus principal component 2. So how you can read that here you can see that the most of the, you can say that each dot, here we have seen different dots or small circle. So you can say that these circles are actually the number of farms. So number of farms, here the darkest green, it means you can say that it is mostly impacted by the or comes into the principal component 1. Now here you can see that arrow, these arrow is the again you can say that one variable, it reflect that the direction. So here if I can say that here this is showing irrigation hours, it is showing rainfall. So it says that which principal component is most associated with it. Now here if I can say that this irrigation hours, this is left side of 0, it means into the negative one. So we can say that it is related to the PC2, principal component 2. And now here if I can say that irrigation is bottom side while the rainfall is upward side, it means these two directions are totally opposite to each other. It means it represent that when there is rainfall, no irrigation required, or if irrigation required, it means no rainfall required. So that's why they represent the opposite direction, while the arrows are going into the similar direction, it means they are, you can say that they impact each other. Now here you can see that mostly they are going through this principal component, it means they are purely impacted by the soil pH, phosphorus and nitrogen. Now we can go for the same principal component analysis for the patient health profile. So here we have considered around 40 patients. Then here we have considered 9 variables. So that variables are age, BMI, systolic BP, diastolic BP, glucose, mg, all that. Now we will do the similar kind of things that we have did for the agriculture data. So here first we have uploaded the data. Now here we can see that we have represented, we are considering 40 data set. So for here we have named patient 1, patient 2, patient 3. So first 10 data set, sorry, excuse me. So then we have that variables as age, BMI, different kind of BPs, glucose, or all that. Then we have descriptive statistics. It means that we have to understand for each variable, suppose for age, do we have total 40? Yes, we have all 40 information. Similarly, for BMI, do we have all 40 counts? Yes, you can see that we have all 40 counts. Then we calculated the mean. We checked the mean for the age, BMI, and all that. Similarly, we considered the standard deviation, then mean of the age, then minimum of the age, maximum age, and all that. Then again, the next step is that we have to find the covariance, variance, and cumulative. So here we can say that again we applied. The only difference is that there our data set was formed. Now here our data set is, this is our data for biomedical. So just we are changing the data set, we are changing the data frame that we are using. Otherwise, we are doing the similar process. Now here we can see that the first principal component variance is 45, around 45%, while the second principal component, the variance is 15%, but the cumulative covariance is, cumulative variance is around 61%. Then using the PCA3, PC3, 10% and total around 70%. So this way we can proceed and we will check that how many principal components are required, or we can get the result for that. So here again, we can see that the similar that we will use the data, upload the data, and then for the PC component, we have plot. Now here again, the principal component versus eigenvalue. We consider the same rule that we consider eigenvalue for one. So you can say that here principal component 1, 2, 3 we will consider, and we will get around 80 to 90%. Like here, 4 principal components, it gives around 80% of cumulative variance. Now next step is that we have to again check for the relation. So here instead of calculating that indivisible variables, I'm just skipping that step and we can directly checking for the heat map for the variable with the principal component. Now see here, principal component, first 3 principal components with the variables. Now here you can say that how these variables, different variables. Now see, age in the first principal component have 0.444. Here you can see that how they much involve or related to the specific principal component, their involvement. BMI, body mass index in principal component, you can see that is 0.257. While systolic BP 0.415, you can say that's the highest one. Similarly, for the principal component 2, we can say that white blood cell count, it affects the principal component at most is 0.536. Similarly, diastolic BP 0.517. Similarly, for the principal component, we can say that how the highest is that white blood cell count. Then next we are going to understand that yes, it is executing now here. Yes. So there, the way we have completed the plot here again, we have considered now since we have patient of different age group. So we have divided that age group between 0 to, you can say that 45, then 45 to 60, then 60 or more than 60. Now we have defined different colors, that what are the colors, specific color to that particular age group, and then we have make them as a group. The next, if you can see here, this is the data. Now we can easily understand from here that if you can see that the red color, so red color is that high risk or abnormal blood when we are considering for the blood composition, and here it's a low risk. Green, it means low risk and normal blood. So here this is PC1, cardiometabolic risk. This is, and principal component is blood composition. So earlier, instead of one specific variable, we have constructed the principal component. That principal component is the combination of 2, 3 or 4 different variables, and then we mark them as a different name. So here, for the first principal component here, you can see that most of these are red. It means they are highly risk. and they all are senior citizen. Here you can say that more than 60 age. So it represents that the senior citizen or the person whose age is higher than 60, the chances of that cardiometabolic risk is high. They all are, you can see that it is in the PC1 component. Similarly, if you can see the middle aged, so all that middle aged are in between, you can see that -2 to +2 principal component 1, and you can say that PC2, it means blood composition. So since they are in the mid of that range, so you can say that they are not actually very much impact or affected, but yes, they are. And the green one, you can say that the green one is the low risk and normal blood, and here they are totally related to the principal component 2. Now our next is that cluster analysis. That is very important, that how now we understand that where is the problem, what is the problem. Now our idea is to making them into two or three different groups. So here that we can use that Euclidean distance, that is most common. Then we have another formula, Manhattan distance, then Minkowski distance. So we will use k-mean clustering. So for the problems, we have to find out what is the k, what could be the value of k. So for that, we have again we use the Silhat problem, and then we will find the value of k. So here we can go with the example one. With the same example, now here you can see that this is the information about all 30 firms. And since we have already done the principal component, so here that PC 1, 2, 3 are divided into zone A, zone B, and zone C. What is zone A? Zone A is fertile and irrigated. Zone B is dry and low fertility, and zone C is rain-fed and moderated. So here, based on our principal component analysis that we already did, we can get the information about all the forms with their cluster labels. Now, based on these clusters label, we are going to make a 3 different clusters of all these fields. It's executing, yes. Wait. Wait, why it is, let me. Just give me a second, it's getting an error, so. Okay, so we have, as we discussed that we will add, based on that clustering label, we have already get that principal component A, 1, 2, 3. So principal component 1, we can represent as zone A, principal component B as zone B, and principal component 3 as zone C. So based on that, now here, what we are going to do that we have prepared a normalized cluster profile for agriculture zone. So here you can say that for the soil pH, can you see that when we are talking about the soil pH variable, So this form has no zone A. It means it is not fertilized and irrigated. While if you can see that here for the temperature variable, so you can see that here we have zone A and zone C, but there is no dry and low fertilized. Why? Because as we have already calculated or divided that forms into different clusters, and based on that we can easily visualize the data instead of in the tabular form. Now see here, this is the, you can say that as we are saying that clustering, it means that we are making that data into different groups. So here you can easily see that all the groups A is written as green, in a green dot. So it is PCA1, PCA2, that is matched. Then red, zone B, dry and low fertility. You can easily see that here, if the green is high level irrigated and all that, so this is totally different. And then we have another cluster of rained and moderated, zone C. Now here, when we are using k-mean clustering, how the value of k is divided? So for that only we can use some different algorithm, and here you can see that the based on zone A, zone C, and zone B, what is the yield? So you can say that for zone A it is around 14, zone C it is around 18, 17 to 18, and then zone B it is around 15. So highest zone we can say that from zone we can see it is the zone C. Then we have used here hierarchical clustering also. So but before that, let me explain you the for the medical one, that is important. So for the medical, you can see that we have already divided the patient into different group or cluster. You can say that principal components based on the based on the risk level. So here red represent high risk, escalate to physician. Green dot, low risk, stable profile. So there we have already reflected that the green, it means no, abnormal blood and sorry, green normal blood low risk, red abnormal blood high risk. So here we just make them as a two different categories. Now here we are counting that how many patients are with the higher risk, 18, how many patients with the low risk, 11, how many as a moderate risk, that is 11. So based on that clustering, you can see that here we have clustered into different groups. That groups are green for low, red for high risk, and this is for the moderate risk. Thank you. I think I should end it here.